Today we've got Nadia Figueroa, who will be talking about learning techniques applied to physical human-robot interaction, which we are very excited to hear about. Nadia did her PhD with Aude Billard at EPFL, who many of us know, and she's currently doing a postdoc with Julie Shaw at MIT, which also many of us know her as well. She has been nominated for a large variety of awards. Let me see if I can bring this up. For her PhD, actually I can't find it. I'll try to go from my memory. There was the George Derault PhD award that she was nominated for. There was, I think there were 3 year PhD or EPFL PhD awards, which is actually quite amazing, as well as best paper at RSS, which is impressive. So anyway, I will leave the rest of the time to Nadia. Please take over.
Right. Thank you, Mark, for that introduction. I'll start sharing my screen. All right. Can you all see the screen? All good?
No, this is the presentation view, presenter view. You want to switch?
Oh, sorry about that. And there you go.
Yep, looks good.
All right, thank you. All right, thank you so much again, Mark, for the introduction. I'm delighted to be here and talk to you today about the main themes in my research, which focus on endowing robots with the capabilities of learning from humans in an efficient way, while at the same time being able to physically collaborate and interact in a safe manner, as can be seen in this video, where a robot manipulator is performing a pick and place task while allowing the human operator to safely modify and adapt the task on the go. And the work that I'm presenting today highlights some of the contributions from my PhD thesis, which I did at EPFL in Switzerland, as well as some of my ongoing work here at MIT. So my research is motivated by this vision that one day we will have robots working alongside humans in a myriad of tasks, from teaching robots to perform complex tasks like sorting, cleaning, or manipulating objects in factories, warehouses, and even households, to physically collaborating with them to perform a joint task, such as handing over large objects or even cleaning a shelf from your room. So while all of these tasks seem quite trivial for humans to perform, they are actually quite complex as they require for robots, as they require detailed knowledge about the task goals, the structure of the task, and also the environment around the robot. Now, thanks to the advent of collaborative robots and compliant control schemes, one can actually physically guide the robot to perform a task, as I showed in some of the videos on the top. However, purely imitating or replaying such guided demonstrations is not sufficient for a robot to perform it robustly in dynamic environments where both the locations of the objects or even the robot state itself might change. Further, when the task requires the human to be in the loop, we have now another level of complexity, as the robot should be able to adapt also to the changes imposed by the human or the environment, while still being able to guarantee some sort of task completion or success. So for robots to truly be adopted in such scenarios, we must minimize the time and effort it takes a human to train a robot. We also want the robots to be adaptive and reactive to changes imposed by the human or by other agents, while at the same time guaranteeing task completion. And finally, we also want to guarantee safety for both the human and the robots while they are physically interacting or simply in close proximity with each other. So if we think of all of these objectives from an optimization perspective, it might seem quite challenging to guarantee all of them at once, as they might have contradicting and even unspecified goals or objectives. So if we consider these 2 objectives, which focus on guaranteeing robustness and adaptability and safety, these properties can be inherently addressed by concepts and tools from control theory. such as the analysis of feedback control systems, state estimation, stability theory, and dynamical systems. On the other hand, in order to achieve efficient teaching, if we are able to demonstrate the task to the robot, then we can use techniques from machine learning to learn a model of the task that can then be used to control the robot to generate the desired motion or the interactive behavior that we desire. Now, using machine learning to teach robots how to perform a task is not a novel idea. Much research in the field has focused on developing deep reinforcement learning or imitation learning schemes that have allowed robots to learn to perform manipulation tasks with very impressive results. However, such techniques are not necessarily efficient, as they require either model selection heuristics to find out optimal parameters for the models that are learned of the task. Some require lots of data and training time to learn simple behaviors such as reaching or grasping. And furthermore, thinking about the objectives that I posed in physical human-robot interactions, most of these models of the task or policies that are learned do not really guarantee these robustness to changes in the task or to even consider the human in the loop or in the vicinity of the robots. So in order to properly use, I propose in order to properly use machine learning techniques to teach robots tasks through demonstrations while providing both safety and robustness guarantees. In my research, I proposed techniques that seamlessly blend tools from these two fields, from control theory and machine learning. So specifically, to learn models of motion of the robot that are adaptive, we assume that the motion of the robot and the human is driven by an autonomous dynamical system of the following form, where x can be the position of a robot, x dot is the velocity, and f of x is this first order differential equation, which describes the evolution of the state variable x towards a target x star. So here we specifically focus on goal-oriented dynamical systems with the single target. And to ensure that convergence and stability, we can basically derive constraints using Lyapunov theory on the parameters of these dynamical system functions. So what are the tangible benefits of using this control theoretic formulation to generate robot motion? Well, first of all, computation time is incredibly fast, which enables us to produce extremely fast and adaptive behaviors such as catching objects in flight. And also, not only can we adapt to changes in the task, such as the video that I showed at the beginning, but also to unwanted perturbations, for example, allowing perturbations from the human to happen, but finalizing the task once a perturbation is gone. So the main idea here is to learn these autonomous dynamical systems that generate the motion of the robot from data generated by the human, so we can provide all of these desirable guarantees while being efficient when transferring the task to the robot. So in the rest of the talk, I will show how that by using this dynamical system-based formulation to generate the motion of a robot, and then coupling it with the impedance control laws and optimization techniques, we can actually achieve all of the objectives with one single approach or framework. And this is quite cool because it's not really limited to a specific domain or a set of tasks or behaviors that a robot can do. For example, we have applied this approach to learning tasks from a high-level perspective, such as learning the structure of a complex manipulation task that requires a repetition of a sequence of actions, to learning tasks that require continuous encoding of a complex motion. And even we even propose techniques to couple and coordinate multiple robots and humanoids with each other and with humans simply by formulating autonomous dynamical systems that couple and coordinate each other, coordinate the robots with each other. So let's dive in. I will begin by describing an approach to learn complex sequential tasks from unstructured and unconstrained demonstrations. So such tasks are those that must follow a sequence of discrete actions in order to accomplish a high-level goal, such as wiping a door fender or a rim. or tasks that can even change the state of a deformable object, such as rolling a pizza dough or peeling a vegetable. So classically, to learn these tasks, one must first segment the collected data into a discrete set of actions and learn their appropriate sequencing to accomplish those actions. So the data that we collect are basically kinematic and dynamic variables, so position, orientation, velocities, forces, torques that can be sensed on the end effector or tool of the robot. And once we gather this data from different demonstrations, then we try to basically understand and decompose this data into a sequence of actions where we then learn a specific action model for each of the tasks. So we can learn a motion model, we can learn a force profile or a stiffness profile, and then we sequence them all in such that we can perform the task with the robot. So going back to the definition of these unstructured and unconstrained demonstrations, an unstructured demonstration is where the human is just naturally performing the task without predefined number of actions, without predefining the sequence, or even the predefining anything, basically just like a natural demonstration that a human might do, like in the video that I'm showing. And by unconstrained demonstration, I refer to those that are not constrained to be spatially or temporally identical, as shown in these videos, where both the position and the orientations of the target object that is being cleaned is changing throughout the demonstration. So learning the structure of these type of tasks, of demonstrations, is important because they represent the most natural way a human will perform a task, making the task transfer much more efficient. So why is this problem so challenging? Well, here I show you a 2 time series. So this is what the data looks like that we collect from 2 different demonstrations of the same task. The shaded colors represent the expected or ground truth segmentation or actions that we hope that an algorithm would extract and find that they are similar throughout the 2 demonstrations. Of course, just by looking at these time series, it's quite difficult even for the human eye to find some sort of similarities, for example, between the blue shaded regions from the top and bottom time series, as well as the pink one. But if we look just at the position variable, so XYZ coordinates of this data, which this XYZ coordinates basically represent the Cartesian coordinates of the end effector, we can see that we can see that basically these 2 demonstrations are subject to some geometric transformation that is imposed by the way the human demonstrated the task. So if we apply, for example, the state-of-the-art algorithm that is used for segmentation, which is a Bayesian non-parametric hidden Markov model, for example, where each of the actions are represented by Gaussian distributions on the entire variables, we can see that we actually get some sort of correct segmentation where it defines where one action ends and the other begins. However, there are more states, or there are more actions than expected. And this is because of this inherent geometrical transformation that the demonstrations are subject to. So the problem actually boils down to if we want, for example, S1 and S3 to be classified or to be grouped as the same action, as well as S2 and S3, then what the problem basically boils down to clustering the Gaussian emission models from the output of this hidden Markov model based on how similar their shape is, rather than how close they are in Euclidean space. So to achieve this, we propose this Bayesian non-parametric Gaussian mixture model with a prior that is imposed on the component assignments. And this prior is kind of like parametrized by a novel metric, which defines how similar the covariance matrix of a Gaussian distribution is with respect to the other in an invariant way. So basically invariant to all of these geometric transformations that the data might be subject to. So this metric, which I call the spectral polytope covariance metric, is nothing but basically a comparison or an analysis of the eigenvectors and eigenvalues of the covariance matrices of our Gaussian distributions. For example, let's say S1 and S2 are the two covariance matrices of two different Gaussian distributions, and which can be graphically seen as these ellipsoids. So to measure the similarity between them, we actually analyze this polytope, spectral polytope, which is actually the convex hull of the endpoints of the eigenvectors scaled by their eigenvalues. So if we look deeper into now, since we have now like minimized the complexity of, instead of trying to find similarity of ellipsoids or hyperellipsoids, we want to find similarity between these spectral polytopes. So in order to do that, I use the concept of homotheity. So basically the idea is if two of these convex, these spectral polytopes are homothetic with respect to each other, then that means that the covariance matrix is similar in shape. And if they're not similar, then that means that the covariance matrices are not similar. So in order to, so here you can see two similar covariance matrices which are homothetic, and here we can see two that are not. So in order to actually find the measure of this homotheity, what we do is we basically compute the relative we compute the relative ratio between the aligned eigenvalues of the corresponding eigenvectors. And this gives us kind of like a measure of how homothetic one polytope is with respect to the other. So for example, if we have, if two of the axes of are similar, have a similar number, but one of them doesn't, then it means that these two polytopes are not homothetic. Whereas when we have a uniform relative ratio between all the eigenvalues, then we can define these two polytopes as homothetic. So now based on this concept, we derive this metric, which is basically the covariance, the relative ratio between the variation between all of these relative ratios. So once we have this metric and we impose it into this more or less standard clustering scheme, we can see that we can actually infer the optimal number of covariance matrix clusters via sampling. So there's no need of human intervention and any type of heuristics, while ensuring that the covariance matrices in each cluster are similar in shape. So here the idea is, instead of using like standard Euclidean metrics, which will not work on this type of data, we impose the metric that is more physically consistent to the data and to the problem that we're trying to solve. So here we can see that our proposed approach is capable of providing these segmentations comparable to ground truth for both of the wiping tasks, so for the fender and for the rim task as well. Now, in the segmentation step, there's a chat. Okay, Dinesh asked, is each Gaussian in the mixture intended to model a segment of the demonstrations? Yes, it is. Okay, so in the segmentation step, okay, so now that we have like we were capable of extracting all of the segmentation and the actual number of actions that are in each of our demonstrations, then how do we use this to control? How do we now use this data that we inferred from how do you use the information that we inferred from the data to control the robot and to actually perform the task? So first of all, we infer the action sequence from the transition probabilities of the hidden Markov model, because this is something that is kind of like embedded within the HMM. So it gives us this this very nice like probabilistic representation of the transitions between the different actions, so we can infer what's the optimal action sequence from the demonstrations. And then once we know what's the optimal action sequence, then we can learn action models from the segmented data. And here is where we use a dynamical system to represent each of these actions. In this case, we use a dynamical system that was proposed in previous work, which is a constrained Gaussian mixture regression that ensures stability and convergence to the target. So basically, for each of the segmented actions, we have we learn these let's say motion primitives, or which are represented as these autonomous dynamical systems which reach a defined target. And then depending on the requirements of each of these sub actions, we can also learn, for example, a force profile, so how much force the robot should apply while following this dynamical system motion generator, as well as the stiffness modulation function, which allows us to modulate the stiffness when transitioning between the different actions. And then once we have learned all of these models, then we feed them to this hybrid impedance control law in order to be able to perform the task. So here in this video, I show now the execution of this of the task that was learned. So it must be noted that I only taught one of these robots, so the one on the top right. I gave the demonstrations with that one. And the cool thing about this is, since everything is learned in the task space, so like in the Cartesian coordinates with respect to the objects, we can actually transfer the task that was learned from one robot to a task to another robot, as you see in this video. And then here, this is another experiment where I actually scale this algorithm to a bimanual task. And here, the modifications to the learning pipeline were quite minimal. So basically, what happened now is that we now, instead of having instead of having like 7 dimensions, we have now like 14. And no, that's not true. We have 13 first for positions and orientation, forces and torques for each of the arms. So now what happens is that we have much more variables, but at the end of the day, the data, the demonstration is the same. We just have a little bit more of different number of actions and sequences. So with minor modifications to the algorithm, we were capable of also teaching a robot to peel a vegetable with 2 arms. So now I will introduce the second set of contributions that focus on learning complex tasks that require the robot to follow now a highly nonlinear path in a continuous manner. So in this section, we no longer want to discretize the task into simpler set of sub actions. We actually want the robot to be able to perform a continuous task that has some sort of constraints basically on the trajectory level, so like some nonlinearities on the trajectories. So to recall, in the previous contribution, I really just glossed over this, but we use this dynamical system which is called SEDS, or it's basically a constrained Gaussian mixture regression, which already has the stability and convergence guarantees that I want. So why don't we just use this approach to encode these type of more nonlinear behaviors? Well, if we try to learn these type of data, these type of demonstrations using this previous algorithm, we will get the following results. So on the bottom right, you see the red trajectories are the demonstrations of the task that I want the robot to do. So basically go and pick different objects, different blocks from one bin, pass them through this kind of like inspection tunnel, and then place them on a target. And the black trajectories are actually the execution of this learned dynamical system that is constrained for being stable and guaranteeing convergence to the target. So here we can see that the trajectories from this learned dynamical system, they actually, all of them converge to the target, but they don't reproduce the highly nonlinear motions at all. So why is this happening? Well, if we go a little bit deeper into how the parameters of this function are learned, I will show you that for this specific type of learning algorithm, they used a quadratic Lyapunov function, which is one of like the simplest Lyapunov functions that are used. So in order to, which basically imposes a lot of restrictions on how nonlinear the motion can be, how nonlinear the motion that is going to be reproduced can be. So in this case, I proposed a less restrictive Lyapunov function to derive stability constraints of these dynamical systems. So basically, just introducing these P matrix, which would be like a symmetric positive definite matrix, we kind of like flattens or creates now, instead of having a circular Lyapunov function around a target, like we have a more ellipsoidal one, where we allow for more nonlinearities in the state space, where we want the robot to be more nonlinear, to follow a more nonlinear trajectory. So to give a little bit more context in this, so let's say, what does this function f of x now look like? So given a set of these nonlinear trajectories, we encode them by representing the dynamical system as a mixture of linear dynamical systems. And these systems are all weighted by this mixing function gamma, which is a scalar function that must be bounded between 0 and 1, and with the constraint that it should sum up to 1, basically. So this gamma function actually indicates in which regions of the state space the linear systems are active, and then mixes them in order to create this smooth transition in between them. So in order, given the requirements of this gamma function, we parameterize it with the Gaussian mixture model, learned solely on the position measurements given by the demonstrations. And so given the mixing function, we now have to learn the linear system parameters. So we do this by basically a non-convex semi-definite program, where we minimize the mean square error of the velocities from the demonstrations and the ones that are given by the dynamical system, subject to the stability constraints that are derived by this new Lyapunov function. So one of the caveats of this method is that the reproduction accuracy of the dynamical system itself relies heavily on the number of Gaussians and how they are placed in the density district in the state space of our trajectories or demonstration. For example, if we use a classical model selection approach to fit a Gaussian mixture model to this data, we would get, for example, the following curve, where we use expectation maximization just to fit different types of Gaussian mixture models with different number of Gaussians, and then we use a typical analysis of, okay, we find that points in the curve, the elbow, which gives us the best trade-off between model complexity and likelihood. So let's say like that we follow that approach, and we say, okay, we choose this model that fitted 5 Gaussians to our data. So now from a density estimation or purely machine learning perspective, these actually seems to be the most optimal fit for these trajectories. So we have minimum number of Gaussians, and the spread and the shape of the trajectory seems to be represented fairly well. However, if we analyze the clusters closely, we see that they actually violate the assumption that we made, that each of these Gaussians should represent or basically defines where a linear dynamical system is being activated. So and these clusters actually contain non-contiguous trajectories and also trajectories in opposite directions. So when we try to now learn one single linear dynamical system on these type of trajectories which have opposite directions and are non-contiguous, then we will get very poor results. So basically we kind of like fall back to the original problem of the original algorithm, where we actually are capable of reaching the targets from anywhere in the state space, but we no longer are capable of like reproducing these very nonlinear trajectories anymore. So in order to alleviate this, we proposed another Bayesian non-parametric Gaussian mixture model clustering scheme, very similar to the first one that I proposed, where we use a prior to kind of like guide the clustering of the points that are going to be like represented by each of the Gaussians by a new physically consistent similarity metric, which not only takes into consideration the locality and the Euclidean sense in the Euclidean space, but also the similarity of their corresponding velocity measurements, which now introduces kind of like a measure of directionality in the clustering scheme. So with this new approach, we can actually infer the number of Gaussians that are necessary to properly represent these trajectories for our dynamical systems via sampling. So again, like no heuristics and no human intervention involved, while ensuring a physically consistent fit on the trajectory data. So with this physically consistent GMM approach and by optimizing the parameterized Lyapunov function, we can encode entire complex tasks in a single dynamical system, as in the videos that will show now. So now, in order, yeah. So here you can see now at the top right. So the kind of like tunnel action, and we also have we can also encode this task of grabbing an object from one shelf and placing it on the bottom. And also we have another experiment where the robot is actually kind of like going to a bio point and pressing a button to turn off and on the lights. Now in all of these videos, I show a lot perturbation. So like I show that the robots are capable of kind of like properly reproducing the task, but I also show that while the robots are reproducing the task, like the human can actually perturb it. So in order to achieve this, we basically exploit the robustness to perturbations that are inherent in the motion generators. By either mechanically compliant, or one can use basically a passive compliant control scheme. So in this case, for these experiments, I used a dynamical system-based impedance control law, which is defined on the top right, for a torque control robot that allows for perturbations while ensuring convergence to the target. So basically, this function f of x, this is a negative velocity feedback control law, where the only thing we have to define is basically our dynamical systems that we learn from our demonstration, and this damping matrix, which acts as kind of like the gains in the different directions of motions that we want the robots to follow. So now let's take a closer look into the behavior of these dynamical systems together with a compliant robot controller. So in all of the videos that I showed before, the underlying behavior can be described as follows, right? So like we have this reference trajectories, which are the red trajectories that we use to learn or shape our dynamical system, which is the blue vector field. Then while these dynamics, while the robot is following these dynamics, we can perturb it. And in any case, the robot will always kind of like go towards the target. However, if we wanted a task that required the robot to actually go back to a reference trajectory, so basically having this trajectory tracking behavior, then this type of motion generator approach wouldn't be so useful, because it's basically inherently robust to these perturbations, but in the sense that it will just follow the next integral line in the vector field, not necessarily go back to the trajectory that was used for demonstration. So is it possible to actually introduce this type of trajectory tracking like behavior, which is generally modeled by using, for example, a time-dependent controller? And in this case, we want to not be time-dependent. We always want to be state-dependent, so that we can conserve or basically keep these nice properties of like robustness to perturbations. So in order to do that, I introduced a new dynamical system where we can actually embed these kind of like stiffness like behavior in the dynamics itself, without having to have kind of like an external controller to be able to like track or regulate the error between the robot and the reference trajectory. So and for example, here in this orange shaded region, that's what I call this kind of like spring-like behavior, where if we want the robot to really follow like more closely a trajectory within this region, then here the vector fields will be reshaped such that they kind of like attract towards a trajectory. And then in the white areas, which are kind of like the global part, there we can just still follow kind of like the vector field that was shaped from the original demonstration. So this dynamical system, we proposed it, and it was called the locally active, globally stable dynamical system, or LAGS. And it has the following form. So basically, it's a combination of the previous approach that I presented, so a mixture of linear systems, which shapes this global vector field around the demonstrations that were given, and achieves and reaches the global target. And then we also have another term, which is another set of local dynamics, where here we basically encode this local attractive behavior, but towards linear parts of the reference trajectory. And then we have this alpha function, which is basically a mixing function, and also has to bound it between 0 and 1. So in basically in the regions where it's 1, the global dynamics or the previous approach will be the one that is guiding the robot, while in the local dynamics, then that's where now the attractive behavior towards the trajectories is going to be active. So by mixing these two, then we can have these kind of like two types of behaviors, where we have a global convergence to a target, but at the same time we can allow to the robot to follow a reference trajectory locally. So here I show an experiment of this formulation being used to follow a reference trajectory of a certain shape, in this case an angle. And so as can be seen, the robot is still compliant. So it's while performing the task, yet in the areas where, in the shaded areas, and in the orange shaded areas where we define where the robot should be stiff or around the trajectory, the robot now becomes a little bit more stiffer, and then actually goes back towards the trajectory. And as you can see here, like we can, with these behaviors of kind of like loops that emerge when the robot is being perturbed, and then it just kind of like goes back to the reference trajectory again. And it's just kind of like trading off these two concepts of allowing a perturbation, but at the same time going back now to what the task actually is, so that we can complete it successfully. So now, so the methods that I proposed actually hold these really nice properties of being like efficient during learning and being able to adapt during task execution. It also allowed us to branch out to other applications that are not necessarily just for robot manipulators or manipulation. So here you can see the same algorithm, the first one that I presented, the global dynamics, being used to drive this semi-autonomous wheelchair, and then in the 2D environment. So basically we can use them as navigation behaviors as well. And also for humanoid robots and navigation. So here we actually learned a lags DS. So here we were trying to show this attractive behavior towards a reference trajectory. In this case, we actually recorded trajectories of the humanoid while we were pulling it towards the target, following these lines on the floor. And as you can see, when we actually perturb the robot and we pull it away from this reference trajectory, the robot kind of like allows for these perturbations. But once we release the robot, then it kind of like starts going back towards the reference trajectory that it was used to shape the dynamical system, and while keeping the same stability and like reactive properties. Now here I'm gonna say that here that this project was in collaboration with Salman, which is the other person in the video, and he was the one in charge of the low-level controller for the humanoid robot, which basically acts as a damper to the system. So for the videos that I showed with these two arms, here we actually formulated a dynamical system that is capable of tracking an object and coordinating two arms or even multiple arms with the moving object that can be either carried by a human or flying towards the workspace of the robots. So here the idea is quite simple. So basically we create a dynamical system for this virtual object, which is always tracking the real object. So here, we just basically have 2 points in 3D space, which are tracking these other 2 points in 3D space, and this dynamical system is coupled with another set of dynamical systems that actually that represent the motion of the robots now that track the virtual object. So basically, once the virtual object is converging to the real object, and the robots converge to the real object as well, because we have kind of like these three dynamical systems coupled in with these equations. So yeah, so this is the formulation of that dual arm dynamics. And here, so here these functions, for example, a of theta. Here, these also can, these are linear system matrices, which can be learned with the approaches that I presented before. So now, considering this problem of now, if we can use these dynamical system formulations to coordinate and generate motion between multiple robots, then we also need to take into account like this problem of okay, so now we need to control for the kinematics of the robots themselves, such that there's no collision between the multiple arms. So here, what we did is actually we proposed in this work a centralized inverse kinematic solver as a QP problem under constraints, and these constraints actually include a self-collision avoidance boundary that was learned from sampling the joint workspace of the robot. So basically, we in an offline phase, we sample all of lots of multiple like configurations of this dual arm setting, and we learn a function which with a classification function which defines if the robots are in collision or not, or not in collision. And using this function, then we can formulate a constraint in an optimization problem such that we can actually avoid self-collision between the arms through a data-driven approach, which is efficient to compute because we use a sparse formulation here for a support vector machine. And we used it as the underlying level controller in on several of the multi-arm scenarios that I showed. So here you can see some of the capabilities of this approach. So here the idea is that the two robots are actually following kind of like their own dynamical systems that are tracking the two the two markers on the hands of my co-author, and they're tracking basically the markers while at the same time avoiding colliding with each other. And here is another example of when we couple this with a compliant control scheme with these two KUKA arms. You can see that the robots kind of like allow the humans to kind of like guide them towards anywhere in the state space, but as soon as the robots are kind of like close to each other, then they start moving away from collision to basically avoid it, because the underlying low-level controller is this inverse kinematics that uses this learned self-collision avoidance constraint. So so then we extended this approach to also humanoid robots. So like basically to perform pick and place tasks with the same virtual object dynamical system. And here you can see some examples of this approach being implemented on the ICUB robot that is capable of tracking this object. We also have a lot of like kind of like safety schemes where if the object is going away from the workspace of the robot, then the robot kind of like goes back to a standing posture such that it doesn't fall and doesn't have to try to like track the object if it's going really fast. Now, then we also extended this idea of learning self-collision avoidance boundary, or basically like the safe workspace of a robot to humanoid robots. So here you can actually see a projection in 2D of just so basically the red parts of this graph are the collided configurations, and the blue parts are the free space motion. And here you can see, and the yellow dot is basically the position of the hands. And here you can see now the same approach being used on this humanoid. Here is an inverse kinematics without the self-collision avoidance constraints. And then here you can see the ICUB picking up this object while using the self-collision avoidance constraint, and you can see that it kind of like figures out how to go to a different posture without while avoiding colliding with itself. So now to provide this whole body adaptive motion planning with dynamical systems, you can see that, so first I presented kind of like this dynamical system that is capable of coordinating hands and arms with objects such that we can grasp them. And I also showed an example of a robot basically following a dynamical system to walk, so as a navigation behavior. So if we combine the two, we can have like these really nice emerging kind of like reactive behaviors where the robot is basically trying to track this object, but it's adaptive to the changes in the target on the fly. And then once it's near the object, then it's capable of grasping it. And then we also extended this same approach, but now to this more complex scenario where two human robots actually have to grab an object and follow the specific trajectory such that they can grab it from one conveyor belt and place it on the other. And here you can see, like, even if I apply some perturbations, since the dynamical system is this lax, which is the one is stiff around the reference trajectory, then the actual task is being performed correctly by these two humanoid robots. All right. So to summarize, I presented this dynamical system-based kind of like formulation, like framework or approach that enables robots to learn from humans and also collaborate at different levels of abstraction and control, while being efficient and offering stability and safety guarantees. Now, while all of these contributions showed the scalability of this approach to different robotic systems and tasks, what do we actually need to deploy robots with these capabilities outside of the lab, like in our houses, helping us cook and clean, like in the envisioned applications of many robotics institutes? Well, first of all, we must think about the human always, as these robots are envisioned to be in human-centered environments. So what's really important is task learning from humans or from expert data. And we also need to explore more in depth the adaptation capabilities of the learned models or the behavior of the robot with respect to human intentions. And also, so one thing that is really important is safety. For example, how can we provide safety guarantees for both the human and the robot? So what I have presented today offers some solutions that overlap these three objectives, but there is much work left to be done. Specifically, in my past work, in the work that I presented, I actually only imposed or learned two types of constraints. So those related to stability and convergence, and those related to self-collision avoidance. However, to perform any type of manipulation task or task that requires a robot to manipulate objects in these human-centered scenarios, there's a myriad of other type of, let's say, constraints that are present in the task. For example, we have geometric tasks or task constraints, such as the robot has to, for example, move in a straight line or follow a specific surface of an object. We also have contact constraints, such as maintaining a certain amount of force when grasping or an object, or when wiping a table. We also have collision avoidance constraints with external objects or with humans. And we can even have temporal or logical constraints when we are thinking of tasks that are more kind of like high level, which require interaction with other agents, or which require kind of like feedback from other agents. So my future research will focus on generating such type of motion policies that will actually be aware of the robot's environment with parameters that are grounded to these physical and task constraints. And so yeah, and furthermore, one thing that I have not mentioned at all up until now is perception. So how do I make these robots track the objects and move and go towards a moving object? Well, in all of the experiments that I showed, we actually use these beacon systems. So we place markers on all the objects, and obviously that's a limitation when we want to deploy these type of collaborative robots into the real world. So so one interesting direction is like, how can we couple the uncertainty of these sensory systems with these dynamical system motion policies? And also, how can we kind of like learn these motion policies in an adaptive or more like online way? So yeah, if you want to learn more about the dynamical, about these approaches that are presented today, especially the contributions on learning the nonlinear dynamics, you can find videos and lectures and exercises in MATLAB that we presented in ICRA 2019 that I organized together with my PhD advisor and former colleagues. And further, if you want to go deeper in the understanding of how dynamical systems can be shaped and formulated to be reactive and adaptive for different applications and robotic systems, together with, again, my PhD advisor and my colleague Sina, we wrote a textbook which will be available by the end of this year. And in this textbook, we actually present all of the theoretical background of these dynamical system-based control approaches in a didactic way, including mathematical exercises and also MATLAB and programming exercises. So all of my code and videos that I showed today are actually available online in my website. So just if you're interested, take a look and shoot me an email, anything. I will be super interested in talking about this research. So thank you so much for your time.
Wonderful. Let's give Dr. Figueroa a hand. And I'd like to open it up to questions. Unfortunately, my neighbors have decided to start their leaf blower, so I'm going to mute. Actually, maybe I can do a quick question while we're waiting. There's one part that was confusing to me in the beginning of your talk when you had the kneading dough and washing. There's and then you showed that you can extract the force profile. That's the one thing. How do you know how much force is being applied to the dough, or when you're pushing?
Okay.
When it's
so there we actually equip the robot with a force torque sensor. So the robot, like the end effector, we put a force torque sensor, and then we have the tool. So then when we collect the data, we kind of like compensate for the tool, but we're capable of actually basically measuring like the amount of force and torque that is being applied. So that's the time series that I showed at the beginning were actually time series of that are given by this force torque sensor, and also the position and the orientation of the end effector.
Okay, I'll kind of add on to Mark's question. And first of all, thanks for the really great talk. I really enjoyed the talk, and the demos were really cool as well.
Thank you.
The pizza dough and the vegetable peeling were particularly impressive to me. And I was actually wondering there, were you on those tasks using the object state as part of your as part of what you were conditioning your policy on, or did you find that it was not even required to do that?
So so that's one thing. So you can either include the object state or not, right? Like, so these are kind of like different ways of learning the task. And in this specific scenario, we didn't include the object state. I included it in the second in the more complex scenario with the peeling. So there I added some features that I didn't mention. I forgot to mention actually, but I was tracking actual color features of the zucchini of the vegetable. So so they can be included in the segmentation algorithm to kind of like disambiguate between the robot not doing anything or the robot actually rotating the zucchini such that it can start like another peel.
Got you. Yeah. So this was also included in the segmentation, and then you also conditioned the controller on it. Is that right?
So the controller, yes. So yeah, the controller is conditioned on purely on the location of the objects. Exactly. Yeah. So from the segmentation, basically, each of the actions kind of like end up at the same point. So we kind of like assume that's like the target or the attractor of that specific of each of these specific actions, and then we just kind of like try to when we execute the task, then we try to find those attractors or place those attractors like on the dough or on the vegetable. And then that's how the dynamical system basically knows how to follow its specific vector field or profile with respect to that target that is placed on the object.
All right, thank you, Nadia.
Maybe I'll ask one as well. Thanks again for the great talk, Nadia. It was I like what Dinesh said. Maybe at a high level, I'm sort of curious what you see the limitations of the dynamical systems-based approach as being. For instance, could you take these concepts and extend them to something like in-hand manipulation or other more complex tasks?
You could extend them to in-hand manipulation, but it depends on how you like how you approach the problem. Like, do you want to use a dynamical system to maybe like predict the motion of the object itself, or maybe like as like the virtual object idea that I use when like grasping an object? Or you can also think of the hands as multiple manipulators, and then just have like these dynamical systems kind of like generate the motion of each of the fingertips. And then you try to obviously there you would need a more kind of like high level layer that plans kind of like where the next target should be, such that now the robot can kind of like, or the fingers can, let's say, follow that specific motion towards that target. So that's specifically kind of like one of the limitations is that it, at least for the approaches that I have been working on, it's more like I only focus on, let's say, a single target, you know, like having the robot go to one target or to reach an object which is basically the same idea. So we were just kind of like trying to track the object position and velocity. So it's kind of like a single place where the action ends. Whereas in real, like more complex tasks, like even you mentioned, like the in-hand manipulation, like there's kind of like a more higher level planning that is involved, that it's not really being introduced into these dynamical systems, because these are more just kind of like low level controllers which are just kind of like shaping or generating the desired trajectory of the robots without really knowing like what the high level goal is, or even if the robot is capable of following these velocities or trajectories. So here in all of the approaches that all experiments that I showed, we assume that the robots are actually capable of following like the actual velocity profiles or the acceleration that these dynamical systems want us to do. It was okay to do that because, I mean, we use KUKA robots, which are really fast, and you can really like push the limits on them. But then if you use maybe like less robust or repeatable robots, then maybe we should take into consideration the now that dynamical or like kinematically infeasibilities of a robot to follow these dynamical systems. And those are some of the limitations that I see. That I'm actually working on something like that to try to see like how can we now introduce these type of let's say infeasibilities, because what I ensure, the only thing that I guarantee with these dynamical systems is that the vector field or the representation of motion of the robot will converge either to a target or to a trajectory, right? Like it's these two things. And but then what happens if the robot kind of like is somewhere outside its own physical limitations? That the dynamical system doesn't know that. So like, how do we introduce now kind of like also these kind of like feasible constraints of that come from the actual robot kinematics?
You mentioned you're thinking about that. Is there any way, do you have like a preview you could share or quick?
So one idea that the first thing that I'm working on right now specifically is on basically bounding the workspace. So as you can see, like these dynamical systems, like they give you velocities, like if you shape them in certain regions of the state space, then they will follow the trajectory very closely. But outside, they will just give you kind of like a linear velocity towards a target. So what if the robot suddenly is shifted or like moved by the human, but the target is still the same? And it's trying to do maybe like some motion where the robot is like at the end, you know, like it's kind of like in a singular configuration. It's at the end, like outside of its own workspace. So there, what I'm trying to do is I'm trying to basically, since we know what the workspace of the robot is, then we can kind of like shape or kind of like enclose the vector field depending on where the robot is. So basically, kind of similar to like the lags approach, where I reshape the vector field such that they follow trajectory. But now if the robot end effector, let's say, is at the limit of its workspace, then you can reshape the vector field as well, so such that it kind of like brings the robot back to its kind of like feasible region, and then it can follow the trajectory again.
We are a little bit after 12. If there's any last burning questions, that would be, I think we could handle them. I have a bunch, but I'm going to reserve them for our individual talk. So, okay, let's give Dr. Nadia Figueroa a hand again. Great job. It was super interesting talk. I thought it was really well done. And Gabby, you can close us out.
Great, thank you so much. Thank you so much, everyone, for joining us today. Please tune in next week, Friday, April 2nd at 11 a.m. Eastern Standard Time to welcome our next Graspon Robotics speaker, Frank Hammond from Georgia Tech. And for upcoming events, please be sure to follow us on social media and check out our website. Thank you again and have a wonderful weekend.